In this episode, we're diving into one of the most fascinating aspects of planetary science: the formation of gas giant planets. These behemoths, like Jupiter and Saturn in our own solar system, are the largest and most massive planets, and they play a defining role in shaping the architecture of planetary systems. Understanding how they form not only informs us about our own solar system's history, but also provides a critical context for interpreting thousands of exoplanets discovered around other stars. Today's content is based on the 2025 Annual Review of Astronomy and Astrophysics article by Ikoma and Kobayashi, which synthesizes decades of theoretical and observational work on this subject. The full reference is linked below. So, how do these giants come to be? Historically, scientists have proposed two competing models for how gas giants form. The first is the disk instability model, which suggests that massive planets form quickly when a region of the protoplanetary disk becomes gravitationally unstable and collapses under its own gravity. This is a top-down approach, essentially forming a planet by fragmenting the gas disk directly. This model is fast, and it may explain some gas giants at wide separations, but it struggles to account for the observed heavy element enrichment in most planets. The second model, the one most widely accepted today, is the core accretion model. This is a bottom-up process. It starts with solid material coalescing to form a core, typically around 10 Earth masses. Once that core is massive enough, it begins to gravitationally attract gas from the surrounding disk. Eventually, the planet crosses a threshold known as the crossover mass, and runaway gas accretion begins, rapidly turning it into a full-fledged gas giant. This model explains several key features: why gas giants contain significant amounts of heavy elements, why there's so much variety in their composition, and why they're more common around metal-rich stars. Still, there are major questions. How fast can cores grow before the disk disappears? What role does migration play? Are these cores formed by accumulating kilometer-sized planetesimals, or are they built by sweeping up smaller, pebble-sized solids? Let's take a closer look at the giants we know best: Jupiter and Saturn. They've been studied extensively through spacecraft like Juno and Cassini. Earlier models assumed that both had similar core masses, about 10 to 20 Earth masses, supporting the idea that a critical core mass was needed to trigger gas accretion. But more recent gravity measurements from Juno and Cassini tell a different story. Jupiter may have a very small, compact core, possibly even no distinct core at all, but its total heavy element content could be as high as 60 Earth masses. Instead of a neat three-layer structure, Jupiter likely has a dilute core, with heavy elements gradually mixed throughout the planet's interior. Saturn also appears to have a dilute core, but its core is slightly more compact and more enriched in heavy elements than Jupiter's. Both have compositional gradients that extend to over half the planet's radius, a complexity not accounted for in older models. And what about their atmospheres? Both are rich in heavy elements. Jupiter's carbon-to-hydrogen ratio is over 3 times the solar value, and it contains enhanced levels of noble gases like argon, krypton, and xenon. Saturn is even more enriched, with a CH ratio over 7 times solar. These enrichments suggest that solid material, likely ices and planetesimals, delivered heavy elements into the atmospheres during formation. Notably, phosphorus and sulfur appear in molecular forms, like phosphine and hydrogen sulfide, indicating their delivery in solid form. Cosmochemical studies of meteorites also offer critical clues. They show that the early solar system had 2 chemically distinct reservoirs: carbonaceous and non-carbonaceous materials. These regions were isolated for several million years. The timing and persistence of this separation suggests that Jupiter formed early, possibly within 1 million years of the solar system's birth, and its growing mass created a gap in the protoplanetary disk that helped maintain this division. That's an extraordinary constraint, and highlights how gas giants don't just respond to their environment, they shape it. Let's now look beyond the solar system. Thousands of exoplanets have been discovered, giving us a statistical handle on gas giant formation. One of the strongest correlations is between stellar metallicity and gas giant occurrence. Metal-rich stars are much more likely to host gas giants. This aligns beautifully with core accretion theory. More heavy elements in the disk mean faster core formation. However, hot Jupiters, gas giants close to their stars, are relatively rare, occurring around less than 1% of Sun-like stars. In contrast, cold Jupiters, located at distances similar to Jupiter's, are far more common. Interestingly, smaller planets like super-Earths and sub-Neptunes are even more prevalent, dominating the exoplanet population, especially at short orbital periods. When we examine gas giant interiors outside the solar system, we often find planets with far more heavy elements than expected. A standout example is HD 1P9026b, a gas giant with over 50 Earth masses of heavy elements, nearly half its total mass. That's a clear vote in favor of core accretion, which naturally leads to such enrichment. There's also a trend: smaller gas giants tend to have a higher fraction of heavy elements. In fact, studies show that while total heavy element mass increases with planet mass, the fraction of heavy elements decreases. This so-called mass metallicity relation provides further support for the diversity predicted by core accretion models. New observations from JWST are opening an unprecedented window into gas giant atmospheres. We've now detected key molecules like water, carbon dioxide, sodium, and sulfur dioxide in several exoplanets. Again, many of these planets have atmospheres rich in heavy elements, sometimes far more than the solar system giants. This suggests that a planet's atmospheric metallicity may be more tightly linked to its overall heavy element content than to its mass alone. But what about the physics behind how planets gather gas? Early in their life, cores are embedded in the gas disk and surrounded by an envelope. If the planet's gravity is strong enough, it holds onto this gas. Once the envelope mass equals the core mass, that's the crossover point, runaway gas accretion begins. The rate of growth depends on the planet's ability to radiate away heat, which in turn depends on the envelope's opacity. Interestingly, newer models show that dust opacity in protoplanetary envelopes is much lower than in interstellar space, allowing for faster cooling and more rapid growth. Another factor is envelope pollution, when solids evaporate inside the envelope, increasing its molecular weight. This causes the envelope to contract, which allows the planet to accrete gas more efficiently. This mechanism can reduce the critical core mass dramatically, sometimes to just a few Earth masses, and may explain why some giants appear to have small cores. However, there's a catch. Hydrodynamic simulations show that in many cases, gas flows into and out of the envelope, a process called recycling. This can prevent the envelope from cooling efficiently, stalling accretion. Radiative transport and buoyancy barriers play critical roles in determining whether a planet crosses this threshold. As a growing planet becomes massive, it begins to carve a gap in the gas disk. Gas must then cross this gap for accretion to continue. The flow becomes three-dimensional and complex, with accretion limited by how much gas is available from the surrounding disk. So how do the cores themselves form? The classical model involves planetesimal accretion, solid bodies colliding and sticking to form a larger core. But the timescales are long, often too long compared to how quickly planets migrate inward. That's where pebble accretion comes in. Small centimeter-to-meter-sized solids spiral inward due to gas drag and can be efficiently swept up by a growing core. This can dramatically speed up core formation. But pebble accretion also faces issues. Efficiency can be low, and forming enough pebbles requires massive disks that may not be common. Recent models take a unified approach, tracking how particles grow from dust to pebbles to planetesimals across the entire disk. These simulations show that rapid core formation within a few 100,000 years is possible under realistic conditions, especially if the planet continuously captures small planetesimals formed by pebble growth. Even after core formation and gas accretion, some major challenges remain. Why do so many failed cores, that is, super-Earths and sub-Neptunes, exist? According to core accretion theory, these should have become gas giants. Several mechanisms might explain this. Perhaps they formed late, when the gas disk was dissipating, or their envelopes were too dusty to cool, or perhaps envelope recycling kept them from ever crossing the runaway threshold. Another challenge is the formation of long-period gas giants, like those detected by direct imaging at tens of astronomical units. Core formation is difficult at these distances. Disk instability might help, but even then, newly formed clumps may migrate inward rapidly. Observations suggest a mix of hot and cold starts for these planets, some forming with high initial entropy, others not. And what about Uranus and Neptune? Their small gas envelopes suggest they formed after most of the disk gas was gone, but forming their cores fast enough remains a major puzzle. Finally, there's the Grand Tack model, which proposes that Jupiter migrated inward and then outward early in solar system history. This explains many features, including the asteroid belt structure, but newer simulations suggest large-scale migrations may be less common than we once thought. In summary, we've made incredible progress in understanding how gas giants form. We now know that Jupiter and Saturn likely have dilute cores enriched with heavy elements. Exoplanet demographics and atmosphere strongly support the core accretion model. New physics, like envelope pollution and recycling, are reshaping our understanding of accretion. Pebble accretion and unified models provide viable paths to fast core growth, and upcoming missions like the Roman Space Telescope, JWST, and Ariel will continue to sharpen our picture of how these giants form and evolve. But big questions remain. How do we build massive cores fast enough? What controls envelope enrichment? Why do so many planets stop short of becoming giants? Thanks for joining us. If you liked the video, don't forget to subscribe. And as always, the full reference for this episode is listed below.